The next speaker of today is Patricia Ribes Metidieri, and she's going to talk about entanglement in Minkowski spacetimes and the source of harvested entanglements. So please, Patricia, go ahead.
Okay, so thank you very much for giving me the opportunity to actually present this work here today. And this work is actually a work done in collaboration with a bunch of people, which you can see here. Let me just start with by telling you a statement that is probably well known in quantum field theory, and that is that entanglement is ubiquitous in quantum field theory. Even the simplest states of the simplest field theories are highly entangled. And from a formal perspective, we know that this statement rests on two different results. On the one hand, the Reeh-Schlieder theorem, which tells us that essentially, if we look at field variables in any one region of Minkowski spacetime, we find that they are entangled with field variables in any other region. And on the other hand, with something that has already been mentioned today, the calculation of entanglement entropy, which tells us that the entanglement between two adjoining regions in Minkowski spacetime is not just large, but ubi-divergent. And well, from a more, let's say, practical perspective, we also know that the entanglement in quantum field theory has to be sufficiently prevalent so that we can actually harvest it, and I will tell you more about it later. So, as I was saying, entanglement is ubiquitous in QFT. But one thing we can ask ourselves is, what does this statement mean in practice? And what I mean by that is that at the core of these two formal results I mentioned, so the Reeh-Schlieder theorem and entanglement entropy calculations, is the fact that quantum fields host infinitely many degrees of freedom, even when we look at regions of the quantum field that are confined in spacetime. However, when we try to extract some observables out of this field, we do so using some kind of physical apparatus, right? Like the one that I have represented here, which are typically made of a finite number of pixels that have finite resolution, that I'm representing here with these arrows. So what I'm trying to say is that in practice, we can access a finite number of degrees of freedom of the field, which you can think of as being an average of the properties that each of these pixels can measure. So in this talk, I'm going to focus on two results that are kind of related and have to do with the following questions. The first one is, how much entanglement is there available when we look at this kind of physically motivated systems with a finite number of degrees of freedom? And the second question is, how is this entanglement distributed in practice? But before I try to answer these questions, let me just give you some more details of how we actually select these observables and how we measure entanglement between them. So let's consider a single degree of freedom of a scalar, the simplest possible theory you can think of. So free massless scalar field in Minkowski spacetime, and we are going to work in the canonical formulation. So then what I'm going to do is I'm going to select a compact region of Minkowski, and there I'm going to select a smoothing function, and I'm going to use this smoothing function to define the so-called smeared field and momentum operators, which are defined basically by averaging the field and momentum operator value distributions with a certain function, which you can think of as being the sensitivity of a one-pixel detector. We will also impose that this function is normalized such that these two operators satisfy canonical commutation relations. With all this, we see that this pair of canonically conjugated operators, we say that it forms or constitutes a single degree of freedom of our field. But if we want to talk about entanglement, we need at least two of these subsystems, but we can proceed in the same way. So what we are going to do is we are going to select another compact region of spacetime, in this case, a space-like separated from the phase, and we can define another function, and we can use this function to define appropriate smeared observables out of it. So basically, we are extracting single degrees of freedom out of one region and another one out of this other region. So this approach has many advantages, among others that we are basically in the regime of quantum mechanics when we work like this, in the sense that the algebra generated by this small degrees of freedom is isomorphic to the algebra generated by a quantum mechanical system with 2 bosonic degrees of freedom. But there is a main difference. So in doing this kind of smoothing procedure, we keep some degrees, we keep some physical information from the field theory. In particular, one important thing is that basically all reduced states that we can compute from this kind of field theory are with a finite number of degrees of freedom are mixed, which means that we cannot use entanglement entropy to quantify the entanglement between the degrees of freedom we extract from this region and this region. Instead, we are going to use logarithmic negativity. Okay? So regarding the first of the questions that I posed for this talk, the first thing we did was basically to try to answer how much entanglement is there between these kind of finite dimensional systems in Minkowski spacetime. So as the easiest thing we can ask, we try to compute entanglement between two such systems like this. So we extracted a single degree of freedom out of this red region, a single degree of freedom out of this gray region that we consider for simplicity to be spheres separated by a certain distance. And in order to define the degrees of freedom here and here, we use a large family of different smoothing functions. So a lot of functions that you can think of. And even some families of functions for which we could obtain analytic results. And the result we found was a bit startling at first, and is that for a large family of smoothing functions, there is no entanglement between these 2 degrees of freedom. Which is, well, shocking at first, but not so much, right? Because the point is that here we just have just 2 degrees of freedom. So maybe these 2 degrees of freedom in general are not enough to capture the entanglement that lies in our quantum field theory. But we soon learned that this is actually something a bit more general, and even if we try to increase the number of degrees of freedom that we are analyzing in configurations such as this one, with tens, hundreds, or thousands of degrees of freedom, is actually entanglement for this kind of finite dimensional systems is actually really hard to capture. Of course, this doesn't mean that there is no entanglement, and in fact, we can find entanglement in configurations such as this one, where we try to compute entanglement between degrees of freedom supported in the red regions and degrees of freedom supported in the gray regions. And we do find it, but again, it is actually difficult to capture, and we have to carefully fine-tune the parameters that we are using in order to do this. So then I'm bringing this up because, as I was mentioning, entanglement between a finite number of degrees of freedom in field theories doesn't seem to be as prevalent as we originally thought. And this is important because then we realized something that was also a surprise at first. And is that for typical modes that we can think of that Unruh-DeWitt detectors couple to, well, basically the entanglement that the detectors are harvesting cannot be coming from pairwise entanglement. But before telling you more about these kind of results, let me maybe summarize the kind of setup that I have in mind with telling you a little bit about entanglement harvesting. So in this setup, I'm considering 2 inertial detectors, A and B, that have a finite spatial profile. And I'm considering that, the detectors are switched on at a certain moment of time and for a finite period, this delta D here. And during this period, they are allowed to interact with a background quantum field, which I've represented with this background image. Now, during the time the detectors are interacting with the field, the interaction is of this sort for completeness, where, as you know, this lambda is the coupling, this mu describes the internal dynamics of the detectors, this psi here is the switching function, so how the detectors are turned on and off. An important part is that the interaction between the detectors and the field happens through this kind of smeared operators at different times, where this function here represents the space-like profile of the detectors. Now, as you also know, we consider that the original state of the detectors and the field, so the total state, before the interaction is just a product state. And we know that under certain conditions after the interaction, we find that part of the entanglement of the field has been swapped into the detectors. Now, why I'm telling you this is because of the following observation, and is that if we analyze carefully what the entanglement being harvested by the detectors is, we see that the only information that the detectors can actually capture from the fields is basically coming from these two families, continuous families of space-like smeared modes. And the result that I just mentioned is that now, if for completeness you want to select a single mode out of this family and any mode of this other family, and you try to compute entanglement between these two modes using the techniques that I described before, you will find that there is no entanglement. But there is no entanglement between these two, nor these two, nor these two, nor any other element of these two families. So, this was actually pretty shocking at first, because then we were asking, well, where is the harvested entanglement actually coming from? After all, if the detectors are able to become entangled, it's because they are being able to access some kind of reservoir of entanglement from the field. So then, of course, we realized that, the fact that there is no pairwise entanglement between these two families of modes doesn't mean that there is no entanglement at all. It just means that the distribution of the entanglement that the detectors are capturing is a bit more subtle. And in particular, it could be happening that there is some sort of multimode entanglement between all the modes in this family, with all the modes in this family, or just some subsets of them. So basically, this is our hypothesis that the detectors might be actually capturing multimode entanglement from these two families of modes. But how can we actually check whether this hypothesis is correct? Well, we decided to do so with doing a direct calculation. So this is what we did. First of all, we selected a discrete number of this family of modes that I was mentioning along the time interval where the detectors are on, such that the different modes are selected at uniformly distributed times. Now, these sort of modes look a little bit weird because, of course, we're in a canonical formulation, but just let me tell you that we can make sense of these elements as elements of the phase space at a reference time, in particular at the time when we turn on the detectors. And we can do so by using the inverse time evolution. So then, this means that we can use this procedure to define two families of n modes, one associated with each detector, in the canonical formulation. The problem of using this procedure is that the resulting modes that we obtain through this are not independent from each other, so two consecutive modes like this one and this one do not commute. And you can see that by looking at this graph, at this figure, when I'm plotting the symplectic products of different, of field, momentum, and field momentum operators, or these kind of modes. Well, in principle, this is a problem because if the modes we are using are not independent, it's even difficult to define what we mean by multimodal entanglement and to define a proper canonical system. In order to get an easy way out, what we did was to use these modes, as I defined, as a first step, and then we tried to orthogonalize them using a symplectic analog of the Gram-Schmidt algorithm that you probably are familiar with. So this is not completely straightforward, but once we did that, we ended up having two families of n modes, one associated with each detector, that are independent of each other and define a proper canonical system. Which means that now we could compute the log negativity between the n modes associated with one detector and the n modes associated with the other detector by using just standard tools. So far so good. And let me tell you our advanced results, and it's that after quite a lot of, hard work, we could find multimodal entanglement. So let me show you what we found, and these are just preliminary results. So here what you are seeing is log negativity, which, as I mentioned, is an entanglement quantifier. By the way, a positive value of log negativity is a sufficient condition for entanglement in this situation. As a function, of the number of modes that we are introducing for each detector. So the interesting thing here starts happening around here. So you see that if we get sufficient number of modes associated with each detector, we do find multimode entanglement, even if there is no pairwise entanglement between any of these modes. And also, very interesting is to notice that here it seems that the log negativity is starting to reach a plateau. But of course, these, as I mentioned, are just preliminary results. And in order to confirm whether or not there is a plateau that would define the maximum entanglement between these two regions, we actually need to extend this plot here. But it is pretty hard to do that in practice. Let me also mention about this graph that we see here some kind of oscillations, which are simply related to the way we split a finite time interval into different ways. So this actually just matters when the number of modes is relatively small. So with this, I would like to give you my conclusions, which is that when we try to analyze entanglement between these kind of physically motivated systems with finite numbers of degrees of freedom, we know that entanglement is there, but it seems to be distributed in a subtle manner, and it is actually quite difficult to capture. In particular, we found that there is no pairwise entanglement between modes of the field that one typically uses for these kind of smeared Unruh-DeWitt detectors in the harvesting protocol. However, we also found that the entanglement that these detectors might be harvesting can come from a multimode entanglement between discrete sets of these modes, of these families of modes. However, a question that we still have to clarify is whether this is the primary mechanism or the primary source of the harvested entanglement that we measure in this protocol. So that's it. Thank you very much for your attention.
Thank you, Patricia. Are there any questions from our Zoom audience? Well, while they come up with questions, let me ask you something then. So when you use the log negativity, as you mentioned, it's true that log negativity is sufficient for confirming that there is entanglement, right? However, it's not a faithful entanglement quantifier unless you are in systems of bipartite systems of qubits or a qubit and a qubit trait, whatever, something like that. So up to which extent can you really claim that there is no entanglement, like between the different pairs, in the sense that you're not really using a faithful entanglement quantifier? Could you talk a little bit about that?
Actually, yes, of course. And actually, the nice thing about this log negativity is that it is faithful in systems when we try to measure entanglement in systems of 1 versus n modes, right? So in this kind of situation, when I was analyzing pairwise entanglement is actually a faithful entanglement measure. It is not a faithful entanglement measure in the sense that it is only sufficient when we look at this situation and we try to analyze multimode entanglement. But then, as I said, still in this case, we do manage to get some log negativity. And then we can conclude safely that there is entanglement in the system.
Amazing, amazing. Thank you so much for your answer.